Okay. Hi, everybody. Thanks so much for the introduction. Thanks so much for the invitation. I'm super impressed with what Rediet and Irene and Kira have been able to do in the last couple of years with MD4SG. It's really become an empire, and it's a huge service to the community. So thank you so much. So I do want to start with an unusual request. I would like to defer questions to the end of the talk because how timing works out in this talk. If you have a crucial clarification question, you will burst if you don't get an answer immediately. You can ask, but other than that, please keep it in mind until the end of the talk, and we should have a few minutes for questions. So what I want to talk to you about today is an approach I'm really excited about for automating decisions on ethical dilemmas using social choice and machine learning. The approach is called virtual democracy. And specifically, I'm going to focus on two domains where this approach will be applied. The first is an autonomous vehicle domain, where the type of decision we want to make is a kind of life or death decision, who will live and who will die in case of an accident. The second domain is more closely aligned with the goals of the workshop. It's a food rescue domain where the type of decisions we will want to make is who should get, which nonprofit organization should get a food donation. So it's also very value-laden decisions that have to do with considerations of fairness and efficiency. So I'm going to start with the autonomous vehicle domain. This is going to be based on joint work with my student Ritesh Nutigatu, a colleague in the CMU Machine Learning Department, Pradeep Ravikumar, and a team of collaborators at the MIT Media Lab led by Iyad Rahwan. Before I get started, though, I do want to make one more caveat. So I've given versions of this talk in the past, and what I've noticed is that people are generally happy until the moment I mention autonomous vehicles, and then all hell breaks loose and the audience becomes an angry mob. The messages keep calm. It's going to be less of a problem because I asked to defer questions to the end, but I don't want you to be upset. So think of this as a proof of concept. And also, this part of the talk, I think, is really useful for pedagogical reasons. It will really help illustrate the approach in contrast with the second part of the talk. You will have philosophical objections. Some of them will be well-grounded. But I think many of them will get an answer in the second part of the talk as well. Okay, so with that, let's get started. So the starting point is this modern incarnation of the classic trolley problem that people have been talking about in the context of self-driving cars. So the idea is that the self-driving car gets into an inevitable accident, let's say because of a brake failure, but it does have the computational capacity to make a decision before the accident actually happens about what to do. And these decisions can involve people's lives. So our collaborators at MIT have been interested in understanding how people make this type of decision, and for that they founded this website that's become pretty famous called Moral Machine that presents visitors with pairwise judgments and dilemmas about what the car should do. So this is a screenshot from the website, just an example dilemma. So here the car can either drive straight and then run into these pedestrians, and you can get the relevant information about the pedestrians. They're crossing on a red light. One is an overweight man, one is a male doctor, and one is a baby. Or the car can swerve, thereby killing all of the passengers, and you can again get some relevant features about the passengers. And the question is, what should the car do? So like I said, Iyad and his team wanted to really understand how people make this decision, and they've really been successful in engaging people and in visiting and participating in this experiment. At the time of our collaboration, it started in 2016, they had 18 million pairwise comparisons from 1.3 million people. By the time the experiment finished last year, they had 40 million pairwise comparisons, and they published a paper in Nature with the results of this experiment. But the starting point of our collaboration was the realization that we can actually use this vast treasure trove of data to not just understand how people make these decisions, but also to automate this type of decision. And that's led to this framework that we've recently been calling virtual democracy. So what I want to do is tell you on a high level what this framework is, the high level steps, and then we'll dive in a bit more detail into some of these steps. So the first step is data collection, where we ask people about their preferences on the type of dilemma that we want to be able to decide. This is the step that was done by our MIT collaborators through the Moral Machine website. The second step is learning, as in machine learning. So here the idea is that we learn a model for the preferences of each person that allows us to predict their preferences even on dilemmas that we haven't seen before. The third step is summarization. The reason we need this is that we're going to need to make decisions very fast in a split second. And we don't have time to go back to the 1.3 million models and consult all of them. So what we do here is we build one concise model of societal preferences that we can work with very quickly at runtime. And finally, step 4 is aggregation. This is the most interesting step and where democracy actually happens. So think about, at runtime, the car is facing some set of alternatives. It can be 10 or 100, any number. And we want to make a decision. The key idea is that what I would ideally want to do is go back to the 1.3 million people and ask them, what would you do in this situation that I'm facing now? I want you to give me your preferences as a ranking over the alternatives. I think of this as a vote. And then I would aggregate all of these votes using a voting rule to get a single choice for the system or a ranking over the choices. So that's the ideal. Of course, this is not feasible because I can't go back at runtime to all of these people. So what we instead do is we use our machine learning models as kind of virtual voters. We use them to predict what the preferences of these people would have been in the situation we're facing right now. And then we aggregate the predicted votes in order to make a decision. So we're basically running this virtual election where the virtual voters are the models that we've built of the different people. So what we've done is we've implemented this kind of pipeline, and that's led to a system that can make decisions using input of the type that you get in Moral Machine. So what I want to do is, like I said, go into a bit more detail about each one of these steps and give you a better idea how it's done. Data collection, there's not much more to say. This is, again, the Moral Machine data set. So let's talk a bit about learning. This is a pretty much not a very interesting step. It's pretty much off-the-shelf technique. So pretty briefly, we use a model from statistics called the Thurston-Musteller model. It's a random utility model. And you have a model like this for every voter. The way it works is that the voter, like if we fix like a set of 3 alternatives in this example, the voter would have a mean utility for each alternative. And when we ask the voter to compare a pair of alternatives or rank the alternatives, we would sample around each one of these means from a normal distribution. So for example, I might take a sample for the red alternative, one for the blue and one for orange. This would give me the ranking blue, orange, red, even though the orange mean is higher than the blue mean. Now the means are represented as the dot product of a feature vector, of a parameter vector beta and a feature vector for the alternative xi. On Moral Machine, there's like 23 features. So it's things like, are these pedestrians or passengers? Are they crossing on a red light or a green light if they're pedestrians? Is the car swerving or driving straight? Plus, the character count, which is, how many characters of different types do you have in the situation. And then our goal is to learn the parameter vector beta. So this is what the learning step does. Okay, so now that we have a Thurston-Musteller model for each voter, I want you to think of it as a distribution over rankings. So we want to think of it as the probability that the voter is associated with any particular ranking. So if you look at voter 1 in this example, we have this Thurston-Musteller model with the normal distributions. And that induces distribution. So for example, the highest probability would be for the ranking on the right, orange, blue, and red. But there's also some chance I'll swap orange and blue, which will give me the ranking blue, orange, red. It's a smaller probability. There's some probability I'll swap blue and red, which will give me orange, red, and blue. There's also a smaller chance for the other rankings. I haven't explicitly put it in the illustration. But of course, there's a positive probability for every ranking. And same for voter 2. There's a different, voter 2 has a different model, which induces a different distribution over rankings. Okay, so let's talk about summarization. What I want you to take away from the slide is not how we do summarization, but what summarization is. Okay, I want to talk about how we do it. So let's go back to our example with 3 alternatives and just 2 voters in the example. And each voter has a distribution over rankings that we have from the model. What I'm interested in is this profile or preference profile, which is the average of these distributions. So think of this as for each ranking, this is the probability that if I sample the random voter and I sample the ranking from the distribution of that voter, I would get the given ranking. Right? So you can think of this as societal preferences. It's kind of the distribution of the population over the different rankings, over the alternatives. Now, remember that each one of the individual voter distributions is induced by a Thurston-Musteller model. What I would ideally want to do is come up with a single summary Thurston-Musteller model that captures these different models for the voters and induces this profile that I'm interested in. Now, this is not exactly possible. There's no one Thurston-Musteller model that exactly summarizes these different models and would exactly induce the distribution that you care about. So what we try to do in this step is kind of do this approximately, come up with a single Thurston-Musteller model that does a good job of summarizing everybody's models and inducing the right profiles. Okay, so let's talk about aggregation, which, like I said, is the most important and interesting step in the way we do the approach. So now, we have again a set of alternatives, of 3 alternatives, and we have this profile, this distribution over rankings. And I want to think of it, like I said, as kind of the fraction of the population that is associated with any particular ranking. So this is a pretty standard input for social choice for voting rules. But the question is, which voting rule should I use? How do I take this information, aggregate it to get a single choice or a ranking? So over the centuries or millennia, hundreds of different interesting voting rules have been proposed. Let me just give you 2 examples to make this concrete. So one is due to Jean-Charles de Bourda, the Chevalier de Bourda. It dates back to the 18th century. And what he suggested is that if we have M alternatives, every voter will give M-1 points to the first position, M-2 points to the second, down to 0 to the last. So with 3 alternatives, it would be 2 points, 1 point, and 0 points. So in this example, blue would have 0.6 times 2 plus 0.4 times 0, which gives you 1.2 points. Orange would have 0.6 times 1 plus 0.4 times 2, which is 1.4, and you can check that red has 0.4 points. So the winner is orange, and the ranking is orange, blue, and red. Another voting rule is even older. It dates back to the 13th century in Ramon Llull. So what he suggested was that for every alternative X, we will give it a point for every other alternative Y, such that a majority of voters rank X above Y. So in this example, a majority of voters is kind of weight 0.5. So you can see that the majority rank blue above both orange and red, so blue has 2 points. A majority ranks orange above red, so orange has 1 point, and no majority ranks red above anybody else, so red has 0 points. So the winner will be blue, and the ranking will be blue, orange, red. Okay, so, so again, there's hundreds of different voting rules, and the big question is, which voting rule should I use to do the aggregation? Once I have these predicted preferences, I want to aggregate them, what should I do? Should I use Bourda? Should I use Llull? Should I use any of the other hundreds of voting rules? And I think this question is actually twofold. There are 2 main kind of criteria that one might care about. So one is, like I said, in our domain, it has to be super fast, so we have to make decisions very quickly. The second is that we're interested in making decisions on ethical dilemmas. So you might ask which voting rule would make the most ethical decisions. And of course, this is a very vague question, like very difficult to formalize. So it turns out that in the setting that is described under the assumptions that we made, I think we can actually give a pretty satisfying answer to this question. So we prove a pretty general theorem. I just want to state a special case for the stuff that I presented. So what we show is that if we're given a profile that's induced by a Thurston-Musteller model that's represented by a parameter vector beta bar, and remember the output of our summarization step was a single Thurston-Musteller model, so we were in this world, then any voting rule satisfying 2 minimal properties, monotonicity and neutrality, would select an alternative that maximizes the dot product of the parameter vector beta bar and the feature vector of the alternative xi. So this is really good news for both of our questions. A, you can compute this thing very fast, right? Just a dot product, so that takes care of doing things super fast. The second is that we don't need to worry about which voting rule to use, because all of the reasonable ones that satisfy monotonicity and neutrality would coincide, would choose the exact same alternative. In particular, Bourda and Llull both satisfy these 2 properties and would choose the same alternative. The example that I showed you on the previous slide is not induced by a Thurston-Musteller model. That's why we did have a difference. So this is kind of really great news under the lossy summarization step that I described. However, a caveat is that when we talk about the next setting in about 30 seconds, then we will not need the summarization step anymore. We won't be able to assume the structure as the input to the aggregation step, and we'll have to rethink how we do aggregation. Okay, great. So let's move on to the second setting, the food rescue setting, which, like I said, is more closely aligned with the goals of the workshop. So I'll spend a bit more time talking about this. And also here we'll take it like almost all the way to practice and talk about empirical results. So this is based on joint work with my students Ansun Kang and Ritesh Nutigatu, my postdocs Alex Thomas, and importantly with Min Kyung Lee, who's here in the room in the back, who's done an amazing job on this project and led a big team of students. So a lot of the stuff they'll talk about is due to her work. Okay, so the starting point of this project is a collaboration with a nonprofit in Pittsburgh called 412 Food Rescue. What they do is they get donations from large stores or supermarkets, and they match them with recipient organizations. So these can be food pantries, soup kitchens, churches, and other nonprofits. And once they decide on the matching, they coordinate volunteers who pick up the food from the donor and drive it over to the recipient. Now the problem, which is kind of also a good thing, is that they've grown a lot in the last couple of years. So at this point, they have hundreds of donor organizations, hundreds of recipient organizations, thousands of volunteers. They're also expanding to other cities. But they still have only very few employees, and typically only one person who's the dispatcher who's actually deciding on these allocations on who should get what. And what they've noticed is that it's been getting very difficult to really spend the time thinking about these decisions. On a busy day, they have something like 100 donations, so it's really not enough time to spend on each donation. So they've been looking for ways to improve this process, either by getting recommendations or partially automating the process. And at some point, we realized that this virtual democracy approach I told you about could be a compelling way of approaching this problem. However, there are several big differences in how we implemented virtual democracy in the previous domain and how we're doing it in this domain. So, let's go over the different steps of the approach. Step one was data collection. Before we had the 1.3 million moral machine users, in this implementation, we decided to just focus on stakeholders in the organization. So these are people who are deeply engaged with the organization, they care deeply about it. So there are going to be much fewer of them, only a couple of dozen that will participate in our system. But on the other hand, it's people who are much more engaged and thoughtful about their participation. The second step, learning, it's basically the same. Both of them are off-the-shelf machine learning and not very interesting. A big difference is in step three. So remember that before, because we had 1.3 million voters and time was of the essence, we needed summarization. Now time is not of the essence. It's definitely okay if we take a few seconds to make a recommendation, and we have only a few dozen voters, so we will not need this step at all, right? Which is also a good thing because we don't need this lossy representation that we needed before. But this will make us completely rethink how we do aggregation, because now our input will, in a sense, be full profiles instead of this very structured summary that we had before. So just to be clear, because we kicked out the summarization step, now the approach will only have 3 steps: data collection, learning, and aggregation. And I think of this as the canonical form of this approach. I think for most applications, you will not need summarization, and time will not be of the essence, so you'll probably only need these 3 steps. Okay, so let's start from data collection. Again, I'll go into more detail for each of these steps. Just to recap, before we had the 1.3 million moral machine users. Now, as I said, we're going to have stakeholders in the organization as our participants. And we think of them as being partitioned among 4 groups. The first is employees of 412 Food Rescue. So we have 3 participants from this group. The second is representatives of donor organizations. We have 6 participants from this group. The third is representatives of recipient organizations. We have 8 participants from this group. And finally, volunteers, who are the people who drive the food around. So we have 6 participants from this group. So to be clear, what we did was we just emailed people from the various groups, asked them to participate, and these are people who volunteered to participate in this process. And they ended up spending many, many hours with Min and her team, giving data, feedback, conducting different workshops, and so on. So these were people who really spent a lot of time with us. Okay, so the next question is, how do we collect their data, right? Before we had these pairwise comparisons that depended on features used in world machine. Now, to be clear, the set of alternatives is the set of recipient organizations. If food donation comes in, the question is which organization should receive it. And the big question, the novel question is, what are the features that should identify a recipient organization? So fortunately, Min has been working with 412 Food Rescue for a number of years, and she has a previous paper in Chi 17 with them, where she conducted interviews, and they told her what are the features they care about for doing allocation, so that really helped us determine which features to use. So if you look at one of these alternatives, the 4 features on the left are things that more or less stay fixed over time. So it's the size of the recipient organization, which is the number of clients that they serve, the level of food access in the neighborhood, which is defined by the US Department of Agriculture, the income level in the neighborhood, and the poverty rate in the neighborhood. On the right, these are features that are specific to this donation, so they're the travel time between the donor and the recipient, when was the last donation to this organization, and the total number of donations received by this organization in the last 3 months. So now that we have the features, we can basically identify an alternative, an organization with the values of these features. And again, we can ask for pairwise comparisons. If you have this organization versus this one with these feature values, what should we do? So these are the pairwise comparisons we presented to our participants, and that's how we collected their data. So I think overall we had ultimately around 100 pairwise comparisons presented to each stakeholder to build their models. It took them about an hour for 50 pairwise comparisons, so this takes quite a bit of time. And in fact, some of them asked to refine their models by giving even more data. So we had a web app where they could actually even give more pairwise comparisons and keep refining their model. Okay. So, and again, I think this is just another way to see that these are people who really spent a lot of time and are very thoughtful about the process. In one place, this thoughtfulness played a role is in the learning step. So again, there's not a lot to say about the technical aspect of how we do learning. I do want to show you some results about accuracy. So what you're seeing here is a subset of the participants, 14 of them, for which we have 2 different models. One is the machine learning model. The other is what we call an explicit rule model. So what we did here is we asked them to build a model manually by giving a score to every possible value of each feature. And then to score an alternative, we sum the scores over the different features, and that allows us to do pairwise comparisons, or I'm not sure what's up with the screen, to do pairwise comparisons or to get rankings. So what you can see is the result for the machine learning model. The accuracy is in red. This is the accuracy of predicting pairwise comparisons. You can see that for half of these participants, it's 90% or above. And even for the others, it's pretty good, except maybe for the 2 outliers on the right. The explicit rule model also did surprisingly well. It had higher accuracy than what I was expecting, but it's not as accurate as the machine learning model. It kind of provides a nice baseline. Okay, so the final step is aggregation, and again, this is the most interesting one, so let's talk about it in a bit more detail, and we have to rethink it, so I'll start from scratch. The ideal thing is what I call the true profile. This is what I would get if I would go to the voters and ask them, what are your preferences over the set of alternatives I'm facing right now? So look at this example with 3 voters and 4 alternatives, right? And I could go to the voters, each one of them would give me a ranking over the 4 alternatives. This is not what we have access to. Instead, what we have access is a noisy version of this true profile that is obtained by using our learned models and predicting the preferences. So for example, for voter 1, I might predict this ranking, which is almost right, but I've flipped the alternatives in positions 1 and 2. And maybe, for voter 2, it's also a pretty accurate prediction, but I've made some other mistake, and similarly for voter 3. So this is the noisy profile, and this is the actual input to my aggregation step. This is the input to the voting rule. Now, what we try to think about is what's a property of a voting rule that we would want that is specific to this setting and would give us guidance in choosing between different voting rules that might all be reasonable. And the one we came up with is this statistical property of robustness to noise. So what we want is that the output ranking, we're going to care about rankings now, that the output ranking of the rule, when it's given the true profile as input, should coincide with the output ranking from the noisy profile. Or in other words, we don't want it to be the case that the noise actually affects, we want to be able to achieve the ideal and give you the same recommendation that we would get if we could actually ask the voters for their true preferences. We don't want the noise to get in the way if possible. So this is kind of the ideal, and in order to make this more concrete, I have to tell you what I mean by noise. Right? So we want to prove some theorems, we have to be more specific about what the noise is. So the model of noise is called the Mallows model for noise. It's a classic model in statistics, but it actually dates all the way back to the 18th century in the work of the Marquis de Condorcet, who's the founding father of social choice theory. So the way the model works is you have some, let's take some voter, they have the true ranking they have in mind, and I want to generate a noisy estimate of it. So what I do is I take every pair of alternatives, and I throw a biased coin with bias p greater than 1/2. If it lands on heads with probability p, I get the alternatives in the right order. If it lands on tails with probability 1 minus p, I get them in the wrong order. So for example, I might compare Children's Hospital and the Salvation Army. I get them in the right order, which means that I rank Children's Hospital above the Salvation Army, like in the true ranking. I compare Children's Hospital and YMCA, I get them in the right order. Children's Hospital and Meals on Wheels, I get them in the wrong order, which means I would rank Meals on Wheels above Children's Hospital, right, like over here. And let's say I get the other comparisons in the right order. So this, this matrix of pairwise comparisons induces this ranking where Meals on Wheels is first, and then Children's Hospital, then YMCA, and then the Salvation Army. Now, probably many of you have noticed that it's not necessarily the case that these independent pairwise comparisons would lead to ranking. The Mallows model kind of takes care of that in an elegant way, but the intuitive way to think about it is if you don't get a ranking, just restart. Okay, so let's stick with this interpretation. The point I really want to make here is that the Mallows model is an unusually good fit with our setting. So like I said, it dates all the way back to Condorcet, who was thinking about in the context of political elections. So he had like a true quality of political candidates by their quality, and voters get noisy estimates of these qualities. So that's obviously unrealistic. But in recent years, people have been thinking about this model in settings where you do have a ground truth. However, it's usually hard to justify why the noise would have this particular structure of making mistakes on pairs. In our case, it actually makes a lot of sense because our algorithms are learning to rank algorithms that get pairwise comparisons as input, and we look at their accuracy on pairwise comparisons. So when I told you the machine learning model has accuracy of 0.9, it basically says, p equals 0.9. Now, there are still some gaps from reality. The fact, for example, that the pairwise comparisons are independent in the model and not really in our setting. But still, this is an unusually good fit with the Mallows model. And I'm saying this as somebody who's worked quite a bit on the Mallows model in the past. Okay, so now that we have the property and we have a formal way of saying it, we can prove some theorems. I'm going to state them very informally. So the first theorem is a positive result that says that for the Bourda count rule, the one due to Bourda that I talked about before with the m-1 points, m-2, and so on, it is robust in the sense that for any true profile, it's unlikely, where the probability is over the noise of the Mallows model, that two alternatives would be ranked differently when Bourda is applied to the true profile and the noisy profile. So we get the robustness property. By contrast, we look at a large family of rules called pairwise majority consistent rules, which in particular includes the Lull rule that we talked about before, and we show that it's not robust in the sense that we want, that there exists a true profile where for any rule in this class, it's likely the two alternatives would be ranked differently when it's applied to the true profile and the noisy profile. So this is nice, I think, because on the one hand it says Bourda is, satisfies the property that we want, and it's kind of a very natural rule, very simple to understand. On the other hand, it says don't take it for granted, because we can show that for many other rules, kind of in one fell swoop, they are not robust in the sense that we want. So Bourda is somewhat unusual in having this property. And partly because of this reason, we implemented Bourda for the aggregation step in our framework. So at this point, I told you how we implement each step in the framework, and that led to a system that can, automates and can make these decisions automatically. But at this point, it's kind of natural to ask, in what sense is the system good, right? So it's doing something pretty subtle, which is taking everybody's opinions into account, taking this participatory approach, looking at all of these different features. But it's natural to ask, for example, okay, but how well does it do on metrics that we might care about, particular metrics? So this is a question that 412 Food Rescue has asked us. And in order to answer it, they gave us some historical data. So it's a couple of months of historical data, 1,500 allocation decisions with all of the relevant features, as well as the allocation decision made by the human dispatcher. So we can compare what we do to the status quo, which is the human dispatcher. And I think the results in this experiment have been extremely encouraging. So we've seen really good results across the board. Let me just give you two examples. So what you're seeing here is kind of the diversity of allocations. So if you look at the blue line, which is the human dispatcher, you can see that what this says is the bottom 30% of organizations received nothing. The bottom 60% received 10% of all donations, and the bottom 80% received 30% of all donations. And you can see that the line for the algorithm is much better. It's still not the ideal, which would be a straight line between 0, 0, and 1, 1, but doing much better than the human dispatcher in this metric. Another example is the efficiency of allocations, which we think of as the travel distance. So by just eyeballing this, you can see that the algorithm is doing much better. There's a much larger spike around smaller travel distances. And in particular, the average travel distance from the algorithm is 5.5 miles versus 6.15 miles for the human dispatcher. So we do see a significant difference. Okay, so of course, the ultimate goal is to actually, this has been a lot of work in many different directions, and the ultimate goal is to get 412 Food Rescue to use this the system. So Min and her team have implemented this as an interface that we can integrate into 412 Food Rescue's interface, and we're in the process of doing that. The crucial point is that the system is designed not in order to replace the human dispatcher, but as a decision support tool. So we want to give recommendations to the human dispatcher, but they would also ultimately make the final decisions. So this is the interface of our system. At the bottom, it's a bit cut in the screenshot, it's the ranking, which is the output of our aggregation step. So these are the list of recipient organizations ranked. When you click one of them, you can get information about that organization and why Borda ranked it the way it did. Okay, so you can get some explanation of how the voting rule works and why it gave the recommendations that it did, which gives you an additional transparency component. So the final thing I want to show you is some feedback from participants. So again, this has been a lot of work with the participants and a lot of feedback that Min and her team collected over a year or a year and a half. And again, I think the feedback has been very encouraging. It's been super cool to see how people reacted to the system. I just want to give you a couple of examples from different stakeholder groups. So for example, one of the donors said that our system, seems quite a bit better than the status quo. If organizations are literally getting forgotten about, which we know is the case from 2 slides ago, then this is huge. One of the volunteers said that this is certainly more fair than somebody sitting at a desk trying to figure it out on their own. It should be the most fair you could get. This is representative of a larger class of comments from people who really bought into the participatory approach and really felt like because everybody's brain power, this is a quote, is being used together, then it's kind of much better than anybody can achieve on their own. A very interesting class of comments was from people who were very suspicious of the algorithm to begin with, but came to really trust the algorithm over the course of working with us and kind of really seeing how the system behaves. So for example, one of the employees said that seeing how the algorithm's construction was broken down into steps and just taking each one at a time made it attainable. Another one of the participants was very suspicious initially and said that they came to trust the algorithm wholeheartedly by the end of the process. So again, this was a very nice thing to see. And finally, there was an interesting step of the process where we showed participants each other's models and the decisions made by the system. And this was seen to really increase trust even in 412 Food Rescue itself and in the shared goal that everybody is working towards. So for example, one of the recipients said that no matter what group or individuals we're feeding, we have the same regard for the food and individuals we're serving. So people really saw that they have shared values and a common cause, and that increased enthusiasm and trust in the whole process in the system. Okay, so let me wrap up with a take-home message. So obviously the main thing I want you to take away from the talk is the idea of virtual democracy and its potential applications. You can kind of summarize virtual democracy as people plus machine learning plus social choice, which gives you a way of automating decisions on potentially ethical dilemmas that is effective. So we saw really good performance on metrics, we saw really good feedback from participants. It's practical in the sense that we have implemented the systems and they work well, and it's transparent. This is something they haven't talked about a lot, but of course, a big part of the discussion of ethical AI these days is transparency and explainability. And a big advantage of this approach compared to many other alternatives you can think of is that it is transparent. People understand Borda, understand how preferences are aggregated. You can give some explanation about why specific choices are made, and I think this is a big source of the power of the system and the reason, a primary reason why people came to trust it. So let me just wrap up with the bibliography. The first part of the talk about autonomous vehicles was based on joint work with Ritesh Nutigato, Neil Gaikwad, Edmond Awad, Sohan D'Souza, Yad Rahwan, and Pradeep Ravikumar, which was in IIII 18. The second part about food rescue is based on two papers. One is with Min and a team of students that she led. I also want to mention Ansun Kang, Ritesh Nutigato, and Alex Psomas, and that's under submission. The second paper about the statistical aspects, just getting the statistical robustness property that I talked about, is a paper that was presented 2 weeks ago in ICML. It's joint work with Ansun Kang, Min, and Alex Psomas. Thank you so much. Sarg?
Very nice talk. So I have a question about the robustness of the voting rules. So here you want the same voting rule to sort of predict its own outcome on what it would have said on the true profile. But if we believe that some voting rule for some reason is more ethical and that voting rule doesn't happen to be robust to noise, can we possibly predict its output using a different voting rule on the noisy profile?
Yeah. Yeah, that's a great question. So I think there is some value in this kind of self-consistency property, right? Like the fact that that, as you know, there are many different, reasons to use a voting rule, including axiomatic properties. So I think a nice aspect of the explainability aspect is the fact that Borda itself is easy to understand. We tell people that we're using Borda, and therefore, like when you have this property, you can say, not only are we using Borda, we're doing the right thing in predicting. So I think there is a big conceptual advantage in that. That said, I think, if you could argue that some voting rule is more ethical in a very concrete sense, there would be a lot of value in trying to solve that question. Yeah.
Absolutely fascinating work. I guess one thing that I was wondering about is your thoughts on, you showed a slide towards the end on actual objectives that people might care about.
Mm-hmm.
I was wondering about the tension or lack thereof between sort of optimizing explicitly for that kind of thing versus the way in which you're doing it.
Yeah.
And, what would happen if you were to explicitly optimize, and then would people trust that, and how different would the results be?
Right. Yeah, interesting. So, yeah, definitely. I've seen people when I've talked about this in the past say, "Oh, shouldn't you just optimize travel distance or things like that?" So there are definitely, some features that make a lot of sense to care about. To me, a possibly natural alternative approach would be to say, we do care about all of these different features. We know from Min's paper people do care about these 7 different features, but maybe we should optimize some combination of these features, so weight them in different ways. So for example, you can imagine a system that elicits weights for the different features from people and tries to directly optimize for that and says, here's my objective. It's this weighted combination of the different things. I think that's definitely a reasonable approach. I think it would lose some of the power of our approach, like the fact, what we saw in the feedback from participants, the fact that it's kind of participatory all the way on every individual decision, the fact that it's using voting and democracy all the way to the end, I think we would lose that aspect. But, definitely, I think that would be a reasonable approach. Yeah. Yeah.
So you showed a nice pairwise comparison that you showed to
Yeah, that's a good question. So I believe we ask which one should receive the donation. You're right that there is a subtlety here, right? So we ultimately want to output a ranking. You're right that, it could have been, you could also think about the question that says, which one would you prioritize, because we are thinking about the ranking. I don't know if that would lead to a different way in which, ultimately, like if I say which one do you prefer, or only one of them will get it, which one should it be? I kind of view them as being very similar, but you're right that there might be a distinction in how people react. Richard?
I have a question about the risk with the information gathering with the moral machine, which is if it becomes known that this is being used for societal decisions of one sort or another, one can imagine that some groups who have strong views one way or another on the
Yeah.
actions would advise their members or actually create fake members to go and vote in a certain direction.
Yeah, so of course, the issue of fake members is something, people have worked on, like Vince, for example, this issue of false name voting. That kind of depends on whether, how much control you have over who votes in the system. For example, in the food rescue domain, we do have control over who the people are. But more generally, I think, I guess one way to address it would be to say, we pick who the voters are, and it's kind of a representative sample. I think there's a second part of the answer might be that it's not easy to directly influence the outcomes in the system, because ultimately you're doing pairwise comparisons, right? And those pairwise comparisons are used to learn models that are kind of indirectly used to make decisions. So I think, it's kind of related to other issues you might worry about, like baking biases into the system, right? So even if it's not something where explicitly some group tries to take over the process, you might say, oh, people have all of these biases, which they would bake into the process. But I think because the input from people is a couple of steps removed from the final decisions, I don't view it as a huge worry, definitely not for something like food rescue. Probably not a huge worry for moral machine given the features, but it's definitely something to keep in mind as we think about other applications. Yeah.
So in both of your models, I think the population preferences was modeled as being unimodal, centered around one permutation. I was wondering, is there a concern that the population might be more bipartisan, like two central permutations, which the preferences are based on, and maybe you want like a mixture of mallows?
Yeah. So we're not quite making that assumption. We have a different. Oh, I see. So when you're talking about after the summary step, basically. Right. Yeah, definitely. So, for example, one thing you could ask is instead of one summary Thurston-Mosteller model, I could have two, right? Which is kind of what you're getting at. So that's both a conceptually and technically interesting question. Conceptually, you could say, even if we have bimodal settings, we could be more accurate. On a technical level, you could say, how accurate can I be if I wanted to capture these different models? I have n different models. How accurately can I capture them with k models? Right? And we don't know the answer to this question. It's a very technically difficult question. I think a very interesting technical open question if you guys want to work on it.
And it might make the second step more difficult.
Exactly. So that would require rethinking the second step.
Let's thank the speaker again.
Thank you.